So the last two chapters, I've told you that we are starting to move into this. Well, we're in it. We are in this thing we called inferential statistics, where we use what we learned in the first half of the year with descriptive statistics and analyzing data. And now we're going to use it to make inferences or make conclusions or see if we have convincing evidence to make certain claims. So chapter 9 is going to be something completely new. We're going to piggyback off of experiments that you do in science classes, but really that's your only background knowledge. I can't even say like you saw this in Algebra 2. You have not seen this before. This is something completely new, and it's called hypothesis testing. So just like in the last unit, we're going to have an intro to hypothesis testing. That will be 9.1. 9.2, we will do hypothesis tests with proportions, and then 9.3 will be hypothesis test with means. And then chapter 10 is going to be a repeat, but we're going to do everything with 2 samples instead of 1 samples. So now it's just kind of using that reference paper, getting very, very, very familiar with that reference paper and all of the formulas and the names of tests or intervals and the conditions that you need to use. So using that reference paper is now going to be very, very, very important. So the big thing is now we're going to be coming up with things called hypothesis. And it's just like in science. Before you do an experiment, you come up with a hypothesis, something that you're going to be investigating. Now in stats, we do this slightly different. So you come up with 2 hypotheses every single time. So the one that has the 0 with it, so this symbol right here, is called your null hypothesis. And what null means is that there's no difference. So like one thing is equal to another thing. There's no difference. That's what you're going to kind of come back to. And that's pretty standard. If you look down here, your null hypothesis, the big thing is it's always, 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 always going to have an equal sign in it. So your null hypothesis will always just have an equal. It's the easiest one to write because you really don't even have to think about it, because you're going to say, oh, the null hypothesis always has an equal sign in it. The alternative hypothesis is actually the one that we're going to be testing every time. So that's saying that something has changed. So there is a preference or a difference. So how we represent that is it can be in 3 different ways. It can be not equal to, it can be greater than, or it can be less than. And I'm going to show you examples of these in just a minute. But for the majority of this, we're going to do one in a second that deals with standard deviation. But pretty much always, you will be talking about proportions or means. You will be always using these symbols. So proportions is always a P. Means is always mu. If I was to handwrite mu, it would look something like that. It's a Greek letter mu. Those are the population symbols for proportions and for means. Your null always has an equals, and your alternative either has a not equal to, a greater than, or less than, depending on what the hypothesis is. Now, we do have something called a one-sided test and a two-sided test. I just said that backwards. This is two-sided, this is one-sided, but we have both. And that just goes on how you're going to be finding those probabilities. So whether you're going to be shading one section or if you're going to be shading 2 sections. And we'll get into that a little bit later, but just be familiar with the fact that there are 1- and 2-sided tests. And basically one-sided are all the equals to and all the greater than or less thans. And the 2-sided is not equal to. So our first example here is just how to write a null and an alternative hypothesis. So you can read through this if you want to. But basically, it says that he's done all this golfing, and he's coming up with a standard deviation of 15 yards. And then he buys this new driver or 7-iron. He buys a new 7-iron, and he wants to see if that decreases his variability. Okay, so it says something in there, more consistent, less variable. So that means he's hitting more consistently. So really straightforward. Remember, in your alternative, you're always going to have that equal. So if there's no difference, if the 7-iron is not improving his consistency, then the standard deviation will stay 15 yards. If it is improving, so this is the one that says it is improving, then that means the variability will decrease or your standard deviation will decrease. Okay, and that's how you write a hypothesis test, or just the first part. And then this would all go in the state portion. If you remember from confidence intervals, state plan do conclude, your hypothesis always goes in the state. Okay, so here's an example, which I think is really cool to see the simulation piece here. So there was an article in the San Gabriel Valley Tribune in 2003, which was forever ago. But anyways, that they were looking to see if most people kiss the right way. And what they mean is when they go in for that kiss, they lean their head to the right. That's the kissing the right way. So somebody sat there. Wouldn't you love to be this observer or this researcher? They sat there and they observed people kissing. And they just noticed which way they tilted their head, whether they tilted their head to the right or to the left. And they found that 83 out of 124, or 66.9% of the couples, tilted their head to the right. So then they said, well, is that weird? Is there a preference? Can we say that that is unusual or not? So they did a simulation first. So if you look over here at all of these dots were trials where I believe they flipped a coin. Because they said if there's no preference, right? If there's no preference, so for my null hypothesis, if there's no preference, then my hypothesis, my proportions should be 0.5. If there is a preference, then my alternative would say P would be greater than 0.5, because that means that people do prefer to tilt their head in a certain way. And P here would represent the proportion of couples who tilt their head to the right. Okay, so each dot represents a coin flip, and then this is what that coin flip looks like. And then what we want to do, again, this is a simulation assuming, so we are assuming that the proportion is 0.5. So that's why they flipped a coin, because there's a 50-50 chance. Okay, so then they looked over here and they said, after we did these 500 trials, what's the probability that we got 83 or more couples that tilted to the right when kissing? So that only dot is that one right there. There's 1 out of 500, which is a 0.002 probability. Now that is unusual. So let's think about what that means. That means assuming that there isn't a preference, assuming that there's not a preference, that you could go left, you could go right, everybody feels comfortable no matter what, then the probability of getting that 83 out of 124 would be unusual. Let me say that one more time. You're assuming that the proportion is 0.5, that there isn't a preference. Proportion is 0.5. Then the probability that we got the sample data that we did is 0.002. That is unusual, which means that this is probably not true, that there is a preference, because when we assumed it was true and then we did our simulation and we collected our data, that gave us an unusual result, which means that we probably have convincing evidence that people do have a preference to go one way or the other way. Okay, I did do this as a binomial distribution too, or a binomial probability. So it says, what is the probability that we would observe 18 or 83 or more couples kissing the right way in a sample of 124 couples? Again, this is the same idea here, where we're saying assume that there's no difference. So that's that 0.5 right there. These should be labeled. 124 is your number of couples. 0.5 is your probability of success. And then 83 to 124 is that CDF thing. Now, this would be if I was using an Inspire. I'm not using it. Well, I did use an Inspire, but I also used the Chromebook. And this is how it would have turned out on the Chromebook there. So again, using that second vars. So that's second vars. And then if you arrow up, there's your binomial CDF. And remember that it always works left to right. So that's why I had to do to 82, because it said 83 or more. And then I used the complement of that by doing 1 minus. Okay, so then it says, what does this probability say about the couple's preference to kiss the right way? So what that means is that, again, we are assuming that the probability is 0.5, that there is not a difference. then the probability of getting 83 out of 124 is really, really small. So therefore, we can conclude, or we have convincing evidence that there might be a preference. Now, you should notice that I'm not using committed words. I always use like convincing evidence. There's probably, never say that there definitely is. That's not what stats does. It just says what could happen. Okay, and then there's two other things we need to talk about here. So that section was pretty much on how to write a hypothesis and kind of what that means. So the other things we have to talk about is a p-value. So a p-value is exactly what we have been saying. So you're assuming that the null is true. So just like in the last one, you're assuming that p equals 0.5, then you're finding the probability of your sample data happening. Okay, and again, if that probability is small, then your null is probably not true. If the probability is larger, then it probably is true, because it's like saying, okay, well, it's true and I got that data, so therefore, or it's true and the probability is big, so therefore it's probably true. So I have a saying here. I don't know, it was kind of funny. A student a couple years ago said that she was in a stats class in college and they were learning about p-values, and she just kept saying in her head, if p is small, we reject the null. And the reason for that is, again, because you're assuming the null is true. If your p is small, that means that the probability of your null being true is probably not true. Okay, so if p-value is smaller than the alpha, alpha is something we usually are going to say is 0.05, but you can actually change that. It's usually 0.05. It could also be 0.1, could be 0.01. Those are some of the common ones, but the most common is the 0.05. So you compare your p to your null. You decide whether p is smaller or the alpha is smaller, and then you say whether you have convincing evidence or not, and you always talk about the alternative. Okay, so I know some of you are like, this is a lot of words. Let's get into this. So back to the kissing example that we just had there. If the estimated p-value, which it was 0.002, what can we conclude? So remember, we're always going to go back and we are going to compare it with an alpha level, which is normally like a 0.05. So in this case, it's small, right? P is 0.002. That is a relatively small number. So usually alpha will be 0.05. If you compare here, we have P is less than alpha. If P is less than alpha, P is small, we reject the null. So if we reject the null, then we just kind of say, oh, that's probably not true, in which case we have convincing evidence. So I should have wrote that differently. I think I say that later on. We have convincing evidence that people probably do have a preference. Okay, now I'm going to erase that because I didn't really want to cross that out. We're going to look at the second one. In the 7 iron example, the estimated p-value was 0.25. And that one, it was, if you remember correctly, it was the standard deviation is equal to, what was it, 15? I think it was. I think I passed it. Yes, equals 15. And then it was less than 15 because it decreased the variability. Okay, so in this one, P is not small because P is greater than 0.05, and we always assume 0.05 if they don't tell us. So here we do not reject the null, so therefore the null is probably true, which means that the new 7 iron does not decrease variability. Okay, because we failed to reject. And notice that I don't say things like we accept. It's just wording. You'll get used to it as we go through more examples. Okay, so here's an example kind of start to finish. So for a second semester project in AP Stats, Zenon, I don't know who Zenon is, but I'm sure he's a nice kid, decided to investigate whether students in his school prefer name brand potato chips to generic potato chips. He randomly selected 50 students and had each one try both types of potato chips in random order. Overall, 32 of the 50, which is a 0.64, students preferred the name brand chips. Zenon performed a significance test using the following hypothesis. So let's talk about these two hypotheses right here. So here is P is equal to, what was it, the proportion of students who prefer name brand chips. Maybe they don't have a Wegmans near them, but we're lucky, and we like our store brand too, probably. But anyways, so P is the proportion of students who prefer the name brand chip. So in his hypothesis test, again, the null, that's where your equals is, because that means there's no difference. Like, it's the same amount of kids that chose the name brand as chose the store brand. No difference. Now, if there is a difference, that means that the proportion of students who prefer the name brand chips is going to be greater than 0.5. Okay, so that's where they're getting those null and alternative hypothesis from. Now, what they want you to do here is they want you to practice with the different alpha levels. So in this first one, they set an alpha level to be 0.05. They're telling you that the p-value is 0.02. So in this case, your p is less than your alpha. P was 0.0239. Alpha is 0.05. Since p is less than alpha, we reject the null. If p is small, we reject the null. If you can say that in your head, you'll never get this wrong. P is small, we reject the null. Therefore, we have convincing evidence that the proportion of students who prefer name brand chips is more than 0.5. Because if you reject the null, you say, yep, you're probably not true, which means that we have convincing evidence that they do prefer the name brand chips. Now, what happens if I use a different alpha level? So these right here, again, people are going to choose alpha levels depending on a few different things, which I'm going to talk about in a moment. But in this one, P, which was the 0.0239, is actually greater than alpha. So P is not small. So we do not, or in other words, we fail to reject the null. When you say you fail to reject, it means that you're accepting it. That is what you're saying is true, in which case you have convincing evidence that the proportion of students who prefer the name brand chips is 0.5, which means that they would not have a preference one way or the other because the proportion is 50-50. Okay? So last but not least, and then you'll get some chances to practice with this, we have errors. So that's the thing with statistics. I said this a moment ago. We don't commit to things in statistics. We don't say this has to be true or this must be true or this is definitely true, because we know that there can be errors because we're only taking samples. We're not taking a census here and collecting all of the possible information. We're taking samples and then using that samples to make inferences. So errors can happen. So we have two types of errors. We have a type 1 error. Type 1 is when you reject the null when the null was true. And then you have a type 2 error, which is if you fail to reject the null so you keep the null when in fact the alternative was true. So you failed to reject the null when you should have, and that would be a type 2. Now, here's my trick for type 1 and type 2 errors. It's right here. So I always do the type 2 error first because I think that that's the easiest, and then I go back and just do the opposite because that's going to be my type 1 error. So for type 2, it's when you fail to, I did do that on purpose. I know that that's not the correct English way to write to, obviously. But a type 2 error is when you fail to reject the null. In other words, you keep the null when you should have rejected it because, in fact, the alternative is probably true. So you have more evidence for the alternative. Again, errors do happen because we're working with samples. Okay, so we're always going to do type 2 first because of that way to remember it. Type 2 is when you fail to reject the null when you should have. Okay, and then last thing, and then we're going to do one example, and this video will be complete. The significance in the type 1 error, whatever your alpha is, that's equal to the probability of a type 1 error. So some of you are like, oh, well, what's the probability of a type 2? The probability of a type 2 is actually what we call beta. You're very rarely, if ever, asked to find the probability of a type 2 error, and they're not complements. They are not complements of one another. So it's not like, okay, so this error right here, let's just go back to that last one where alpha equaled 0.05. So it doesn't mean that you have a 5% chance of making a type 1 error and a 95% chance of making a type 2 error. No, because the majority of the time you're probably going to make the right decision. So they're not complements of one another, but they are inverses of one another. So if you decrease, if your alpha or your probability of type 1 decreases, then your beta, your probability of your type 2 will increase. So they are inverses, but they are not complements. And you can think about that as you go along. And now how you choose your alpha goes with your probability of a type 1 error and how extreme that could be. So of course in class we do, easier ones that aren't going to affect people's health. But in the real world, when they do statistics to make inferences, if there's a possibility of people getting sick or of people dying even, or major consequences, then they're going to play around with that alpha to make sure that the more harmful error doesn't happen, or is less likely to happen. Okay, start to finish. The manager of a fast food restaurant wants to reduce the proportion of drive-through customers who have to wait longer than 2 minutes to receive their food after placing an order. Based on store records, the proportion who have to wait longer than 2 minutes is 0.63. So to reduce this, the manager assigns an additional employee to help assist with drive-through orders. During the next month, the manager will collect a random sample of drive-through times and test the following hypothesis. Okay, so let's go to where we started today's lesson. So we started by figuring out how to write your null and your alternative hypothesis. Remember, your null always has that equal sign. So go up to this. This was what it was before. So they've said that the proportion of customers who have to wait more than 2 minutes is 0.63. Okay, so now this manager has introduced another employee to help to decrease that proportion of customers who have to wait. So that's where that less than came in, because they want to decrease the proportion of customers that have to wait more than 2 minutes. Okay, so that was the first thing that we talked about today, was how to write a null and an alternative hypothesis. Okay, oh, there was what P was. Type 1, type 2 error. Okay, so I said I always start with type 2. So with a type 2 error, remember it's fail to reject the null. So if you fail to reject the null, then you say, I'm going to support the null. My alternative is probably not true, but this is an error. So basically you say that the proportion of customers has not changed. The proportion of customers who have to wait more than 2 minutes has not changed. It stayed 0.63, when in fact, it did decrease. Okay, and that's what it says down there in the red if you want to write that. The consequence of that is that you're saying it hasn't changed, so the manager is going to keep looking for different strategies. They'll probably maybe move that extra person to another location and try something different when the strategy was working. They did decrease the time, but they had made an error. Okay, so that's a type 2 error. And like I said, then I talk about a type 1 error, which is the opposite, which is basically you reject the null. So you say you're not true when in fact it was true. So basically you're saying that the proportion has decreased when in fact it hasn't. And the consequence of that is you're going to stop looking for other strategies because you think that you've already decreased the proportion of customers who have to wait 2 minutes when in fact you have not. And that could lead to some angry customers. Okay, and then the last one is just comparing that alpha to the probability of type 1. So if your alpha level is 0.1, then that means the probability of a type 1 error would be 0.1. So you have about a 10% chance of making a type 1 error. And again, type 1 was when you say that you've decreased the time and you haven't. So you have to figure out which one is worse. Do I want to, is that the better, less extreme, less, is that the, I don't know even how to say it, like the better consequence, I guess. And then you can play around with the alpha level from there. Okay, so we talked about how to write a null and an alternative hypothesis. Remember, a null always has an equal sign in it. Then we talked about what to do with p-values. So I will show you in the next video how to calculate a p-value. You're going to compare that with the alpha. If p is less than alpha, then you reject the null. If P is small, you reject the null. If P is not small, you fail to reject the null. And then the last thing we talked about were type 1 and type 2 errors. Do the type 2 error first because that's the easiest to remember is when you fail to reject. Remember, that means keep when you should have.